side for the whole thing?
I know. I was kind of like working.
All right, so announcements for today is your homework for chapter 28 will be due next Friday because we don't have class on Monday. We'll finish chapter 28 on Wednesday. The homework will be due for the chapter on Friday. All right, so today what we're going to do is we're going to do a number of examples on the board. And you'll have more practice in the homework. But I really want you to really get a good understanding of what's really happening in circuits and a chance to ask some questions here. So we'll do a number of examples today. Let's start out with the following. I have a circuit with a 3-volt battery, 2 identical light bulbs. So what is VAB? What I mean by that is the voltage difference between A and B. This little a and little b. That's here. Okay, explain to your neighbor without using any formulas, just justify your answer. What is VAB in this circuit with 2 identical light bulbs? I'll give you 30 seconds.
Terrible.
All right, so thoughts. What did you come up with here? Yes.
1.5 volts.
Why 1.5?
Because the voltage drop across both light bulbs needs to be the same, and it needs to make the voltage drop in total be 3 volts.
Why?
Because it needs to, on a closed circuit, it needs to return to where it was at the start, and it's like it's always equal to 0.
What rule is that? Yeah, okay, so there's only a couple laws that we need to when we're dealing with circuits. One of the most important is Kirchoff's loop rule, which is really energy conservation. So if you think of conventional current, which is traveling around in the clockwise direction, the flow of positive charge, even though we know for a wire it's actually the negative charge, which is flowing the other way, but positive charge going left is the same thing as negative charge going right. A wire is charge neutral, it's just charges that are moving through the wire, right? Okay, so if positive charge is, let's say I have 1 coulomb of positive charge and it's boosted up by 3 volts, that means it's gained 3 joules of energy by the time it came up to this wire. All right. And positive charge wants to move downhill. It wants to move to lowest amount of electric potential energy. So it falls across the first bulb, it loses some energy, it dissipates some of that electric potential energy. Right? 1 coulomb of charge would have 3 joules. Right? That's what 1 volt is. 3 volts is 3 joules per coulomb. Right? Loses 1.5 joules, has to lose another 1.5 joules to get back to where it starts. It's just like if you were going on a hike and you were racing one of your friends down from the top of one of the mountains around here, right? If you took a different path, you're always going to end up at the same point, right? One way just might take longer. So since these are both identical, they have the same drop. All right, good. Yes?
So VA would be 1.5 and VB would be 0.
Yeah, well, actually, no. Not necessarily. But their difference is 1.5.
Okay.
So hold that thought. We'll come back to that. Okay, so number 2, what if I remove B? What does VAB equal in this case? 30 seconds, convince your neighbor. I just screwed bulb B, I take it out.
Are we assuming the circuit is open now? Or that it's closed and there's just a wire.
Well, so these three are in series.
Okay.
Right now, if I take one of them out, they all go out.
Okay. Make that assumption. Okay.
All right. Right here, I have 3 light bulbs in series. And you can tell they're not burning too brightly. But if I unscrew one of them, the others go out as well. So what would VA be here? It's not 0. 3. Yes, Ryan, why is it 3?
Because you still have the potential difference between positive and negative side of your power source, and that wants to go somewhere.
Right, exactly. So once you unscrew bulb B, there's no more current. So if there's no current, there's no voltage drop across A, so that entire voltage drop is going to be from A to B. Now, when you take B out, it's like you have an open circuit. You don't have a closed circuit, you have no current that's flowing. All right, number 3. Let's say I connect a wire from A to B. Not changing anything else. So all I'm doing is going like that. Okay, 30 seconds. Convince your neighbor. What does VAB equal in this case?
Yeah, it would be 0.
So if just like it was.
All right. Now, I'm going to volunteer to describe what they think happens in this case. Yes.
It's a closed circuit now, so all of the voltage drop occurs at bulb A, so it'd be 0. But on the
Excellent. 0. Now, does bulb A get brighter or dimmer?
brighter,
It gets brighter. Why does it get brighter? There's more current through bulb A because the resistance decreases. So in fact, all the current, if this is an ideal wire, we want to go through here. Now there's less in what we call load resistance across the battery, so it draws more current. Remember, batteries are not a source of constant current, they're a source of constant electric potential. All right, now, number 4 is if let's say I ground point A. Ground A. Okay, so 30 seconds. Try to explain to your neighbor, what do you think would happen in this case? You might be familiar with grounds in electric circuits. What would happen in this case to that voltage difference? Or just the voltage?
Volts at A, and then if you just straight up ground it, so then
A is at 3, B is at 0.
at least that's how
It doesn't matter. All the voltage goes from right now. 3 volts at A and 0 volts at B.
All right, now what does, so a ground
That's not closed.
What changes in this one? Thoughts here. What does a ground do? Yes?
Does it change the amount of charge? Charge is leaving the circuit?
What do you mean by that? Changing the amount of charge?
Like, it's not going to change the current?
How so?
I'm not sure.
Okay, so yeah, so a ground we haven't talked about yet. A ground, all it is, for instance, if you imagined a big electric circuit in a building and driving a big metal stake into the ground is kind of like a large source or a sink of charge. But it's not part of your closed circuit, so it's a way to set a reference point in your circuit. So to get back to your question earlier is, the ground is typically 0 volts. So if you want to set a particular, this is really helpful when you want to connect different circuits together, right? There needs to be a common ground. So when you take, a hard drive and you want to plug it into a computer or things like that, you have to have the same ground point. Otherwise, you can get a spark or a discharge all of a sudden. So grounds are helpful for creating a similar point of electric potential. So this is 0 volts. That would make B negative 1.5 volts. And up here would be 1.5 volts. So the difference is still 1.5. So no current flows into the ground, but it just sets your reference point. It sets your reference point for electric potential.
What did you say was negative 1.5 volts?
Oh, so B would be at negative 1.5 volts. A would be at 0 volts. Up here would be at 1.5 volts. Because it's going to drop 1.5 and it's going to drop another 1.5. So technically, our battery now would look like this. Negative 1.5 and 1.5. Right. The potential difference is still 3 volts. Right? But it's not going from 0 to 3. It's going from negative 1.5 to 3. And that's why normally we're just dealing with potential difference, but when we set a ground, we're saying where is the 0 point for electric potential in the circuit. Yes?
Why wouldn't the current flow through the wire to the ground? Isn't that the path of least resistance? Because the ground would just discharge the circuit, wouldn't it? Wouldn't the ground discharge the circuit?
Well, you can think of when you connect a ground, you're instantaneously, instantaneously there might be a bit of charge to basically equilibrate that point, right? But then this is, charge wants to flow from high potential to low potential. So if I had positive charge here, right, it comes down to here while it's at 0. It has no reason. Think of electric potential again as pressure. It has no reason to want to flow here. It wants to float all the way down.
To the negative potential.
To the negative.
Oh, okay.
And the battery lifts it back up again. It's like a charge elevator.
Okay, thank you.
Yeah, good question. Okay, so that's the concept of electric ground. Very helpful when you're connecting different circuits together. You want a common point, so you don't have like a spark. Like a spark like you saw when I discharged a capacitor. You wouldn't want that to happen every time you plug something in, right? Question?
I still don't really understand why before A it wouldn't be 3 volts, and then you get to A, and it would be 0, and then the rest of the circuit would be 0. Because all that charge is going to the ground.
So think of it just as a reference point, right? Because so in terms of gravity, right? What is y? Think of it as like a coordinate system. Think of where y equals 0. Well, I could call y equals 0 the ground and measure everything with respect to the ground. Or if I'm standing on the table, right? I could say this is y equals 0. And if I'm below the table, I'm at negative height. So the importance is the change, though. So that's all that actually we're really doing here is we're just setting a reference point. Which is kind of a strange thing about energy, is the absolute point doesn't matter. It's only the difference that really matters when you're dealing with potential energy. Yes?
So both bulbs would still light?
Both bulbs would still light. And they'd light exactly the same as they did in part 1. Right? All right, now let's say that I have some light bulbs and I plug them into the electrical outlets. Now, coming from the electrical outlets is 120 volts. Now that 120 volts, 120 volts, it's actually alternating current. It's flipping back and forth at a rate of 60 hertz. And that has to do with power transmission. It's easier to transmit power using AC current. Or it's more efficient, I should say. But let's just say we have 120 volts coming from the outlet here. And I want to connect a couple light bulbs. So, I decide to connect a 60 watt and a 100 watt. So I want you to prepare your vote individually here. And the question is, which one burns brighter? The 60 watt, the 100 watt, or are they burning with the same brightness? I'll give you a moment to think about this. You're going to individually prepare your vote. All right, and so let's get ready here. So 3, 2, 1. Which one do you think it is? Okay, let's take a moment to, we have some of all three responses represented. Try to convince your neighbor which one you think it should be. So watts is a unit of power, joules per second.
Comparison, the other one has a lower resistance
Okay. 10 seconds. Can you prepare your votes? We'll take another vote. All right. So on the count of 3. 3, 2, 1. All right. Now, the majority says B, which is correct. The 100 watt burns brighter. Okay. Now, I'll come back to the explanation here in a moment. But as we're thinking about this, let's also consider the following circuit, where same thing, but the question now is, what, if anything, changes if I connect the 100 and the 60 watt in series? Which one would burn brighter in this case? Give you 15 seconds to think about this individually, which one you think is going to be brighter in this case. Does anything change? All right, so on the count of 3, let's show our votes. Get ready to prepare your vote. So 3, 2, 1. All right, no clear consensus here. So let's try to convince your neighbor which one is correct in this case. So it's no different if you put a 60 watt or 100 watt. If you have a Christmas tree and you have a number of lights in a row, you're going to burn the tree right. All right, so let's take a vote here. So prepare your vote, and 3, 2, 1. So there's a lot of B's, and there's some C's, and the fewest vote is A, but A in fact is correct. The 60 watt burns brighter in this case. Okay. That's A. Yeah. So take a moment. Try to see if that makes. Try to explain that to your neighbor, and then I will try to answer any questions. So I'll give you 30 seconds.
If that were time,
All right, so I'm going to ask Wyatt if he can explain for us. So Wyatt, how did you pick 60 watts here? So everyone listen up to Wyatt here.
So in the first one, the 100 watt bulb has to have a lower resistance if it's going to burn brighter, because that means if it has a lower resistance, then it's going to have more current flowing through it. And in the second one, the voltage drop is going to be proportional to the resistance since they're in series. And since the 60 watt bulb has more resistance, it's going to have a greater voltage drop because current has to stay the same throughout that circuit.
Okay, excellent. Right, let's just write up the formula for power. Right, we have power dissipated through a resistor is I delta V, which using Ohm's law we can also write as I squared R, or delta V squared over R. So why does that, as Wyatt explained, why does the 100 watt bulb burn brighter? Well, it's dissipating 100 joules per second of energy. Not all of that's going to be light. Some of that will be thermal energy. It actually gets warm. Right? Well, it must have lower resistance. If it has lower resistance with the same current through it, it's going to be burning less bright. So when you plug in light bulb in normal household electronics, or sorry, household appliances, why does the 100? So these are incandescent bulbs because you can get LEDs that are several watts, right? Instead of, or much more energy efficient, or light emitting diodes, right? So they're connected in parallel. The bulbs are connected in parallel. Yes.
So how do we know that the 100 watt one has more resistance?
Well, you know now, I guess. Well, so sorry, hang on. The 100 watts, the 100 watt has less resistance. So this one has less R, doesn't it? That's what we found.
How do you find that?
Less R. This is more R. Well, the point here is when you buy a light bulb and it says 100 watts on it, you're probably not thinking about what the resistance is. So if a higher wattage bulb has a lower resistance. That's the key takeaway here. Yes?
So if the power of the 60 watt is higher than the 100 watt in the second one, is it no longer technically a 100 watt bulb because it's not dissipating 100 watts of power?
Excellent point. So if I connect them, this bulb is actually rated to dissipate 60 watts when it's connected across 120 volts or a standard household outlets, right? It's going to dissipate 60 watts. If I connect it in series, if you do the calculation, it actually dissipates 23.44 watts, and then this one, 14.06 watts. It's actually less.
Yeah, what's that calculation?
Okay, so I'll refer you to the notes for the calculation for that. Yes?
So that, like the store, when it says it's a 60 watt, that's just basically measuring resistance, right? The resistance.
It's really telling you something about the resistance.
Okay.
It's really saying the lower the wattage, the higher the resistance, right? Because when it's connected across 120 volts, it doesn't want to dissipate as much energy, right? So it's drawing less current. This one is drawing less current, dissipating less energy because it has a higher resistance. More of the current wants to go through the branch of lesser resistance. Yes?
So could you say that that first circuit is more efficient than the second circuit? Because both bulbs are operating at their max wattage?
Okay, excellent question. So if I take 3 bulbs and I connect them in series across 120 volts, these bulbs are all rated 60, 60, 60 watts. But they're connected in series. They're not dissipating 60 watts each. They're only going to be dissipating 60 watts if I connect them in parallel. So this, in parallel, this is costing more energy. Right? They're dissipating more energy when they're connected in parallel because the effective resistance is less. More current is being drawn from the same fixed voltage source, which is coming from, in this case, the outlets. Good question. All right. Any other questions here? Okay, let's look at another example and about light bulbs. So I'm going to say I have some identical bulbs again. Well, I'm going to go back to this one. Identical bulbs. Okay, so here's my power supply. And I'm going to connect bulb A. I'm going to connect it to bulb B. And then back to ground. And then I'm going to make a switch here with the third bulb, C, so close the switch. I want you to rank the brightness of bulbs. Okay, I'll let you discuss this with your neighbor. You want to think of each of those 3 bulbs. They're identical bulbs. You want to rank them in terms of most bright to least bright. All right, which of these bulbs should be the brightest? A is the brightest. And then what's next? Yeah, B and C are equal to each other, right? Why is A the brightest? We just think of power being dissipated here. If they're identical bulbs, well, they actually have, if they're identical bulbs, they all have the same R. Now, which one has the largest I? A. So it's got to be A that's the brightest, right? Now, B and C, if they're identical bulbs, they have the same resistance. Both paths are going to draw the same current, right? So they're both going to dissipate the same amount of power. And by the way, how much brighter is A going to be than B and C? 4 times, right? Paths B and C have half the current. So I square that, I get a factor of 1/4. Okay, so A is 4 times brighter than B and C. Okay. Open the switch. I want you to think about this individually, and then we're going to take a vote. I open the switch. What happens to bulb A? The brightness of bulb A. Does it brighten, dim, go out, or nothing happen? Nothing just means it stays. Maybe I should say just same. Here, same. Yeah. So take a few seconds individually. You're thinking about what would happen to bulb A. You're making a prediction here. Okay, so prepare your vote. And on the count of 3, so 3, 2, 1. All right, we have a lot of D's and B's, and some A's, a couple A's. So take a moment to convince your neighbor which one should it be. Some disagreement here. All right, so we're going to vote now for A. So on the count of 3, let's prepare our votes, and then we'll show our vote. So 3, 2, 1. All right, there have been some more B's which have emerged, which is correct. So bulb A dims. Okay, the reason bulb A dims is because when you disconnect C, right, C goes out because there's no current through it anymore. It's an open part of the circuit. There's no current flowing through it. It's not dissipating any energy. It just goes out when you open the switch. Right? So now the effective resistance, or the load resistance across the battery, is not 1 R plus 2 R's in parallel. 2 R's in parallel is half the resistance. Now it's R plus R, 2R. So you have more resistance. The battery feels a larger resistance. So there's less current now going through bulb A. It has the same resistance, so it's not burning quite as brightly as it was before. Now remember, in a circuit, imagine the wire is full of electrons. So we're thinking globally, not locally. Everything starts moving at once, right? So one change here doesn't just affect this branch, it affects the whole circuit. When you think circuits, you can't think locally, you have to think globally, the whole circuit. Right? Okay, now, what about B? So think about this individually, and we're going to take an initial vote. What would happen to bulb B? Okay, so let's, on the count of 3, we'll show our vote. 3, 2, 1. All right. A little bit of disagreement here. I want you to convince your neighbor which one it is. Even if you have the same answer as your neighbor, you may not be correct.
And if you take that away, then it's just 2 instead of 2. Yeah, that makes sense.
Okay, let's prepare our votes. All right, on the count of 3, 3, 2, 1. All right. A and D seem to be most popular. A is correct. So it brightens. Bulb B brightens. So about half the class chose brightens. How do you know it brightens? Can you explain the logic here? Yes.
So, well, the overall current in the circuit goes down because the resistance goes up. It no longer has to share current with C, which would have doubled its current, but the overall current went down by a factor less than double, so the overall current to B still went up, and since current's part of the power equation, the brightness went up.
So you're saying the current, the current went down by a factor that was greater than 1/2, or less than 1/2?
Less than.
Less than 1/2. How do you know that?
because it was from so it was 1.5 R to 2 R was the sum of the resistance in the circuit, and I is equal to delta V over R. And so the difference between dividing by 1.5 and 2 and multiplying by 2 is multiplying by 2 is more impact.
Okay, yes, you're correct. So now this is kind of hard to see, so let's just write this on the board. The initial current right? What's the initial current? Well, let's say this battery has a voltage, well, just the voltage of the battery, which we often just call the EMF. EMF is just electromotive force. It's the force which pushes a charge. It's the EMF of the battery. So the initial current using Ohm's law, remember Ohm's law says I equals delta V over R. That's Ohm's law. So the initial current, that is with the switch closed, right, that current is going to be delta V. And we really want to picture a circuit here where we've drawn an equivalent circuit, right, where we're imagining we just have, in a sense, one resistor. And the equivalent resistance here would be, what would the resistance here be? 1.5 R. Because I have one resistor in series with two in parallel. 1.5 R, so the current would just be epsilon over 1.5 R, right, which means that that's the amount of current that is drawn from the battery. But how much current actually goes through bulb B initially? Well, just half of that, right? So the amount of current through bulb B right? Half the amount of current goes, because it has to split between paths B and C. So what about the final current? And by final current, I just mean switch open. Okay, so when the switch is open, now our equivalent circuit, or our simplified circuit, does again look like this. All right, but what's the equivalent resistance now? 2R, right? It increases. So now the current in this circuit is just equal to epsilon over 2R. So how much current goes through B? Same, all of it goes through B now because it has no path to split if we look at the actual circuit. Right? All of it now goes through B. So we have more current going through B. So more current through B. This means more power, which basically means brighter. Okay, and the reasoning that all right, so all of them kind of change here just by opening the switch. It doesn't just affect C; it affects A and B altogether. Questions here? All right, well, let's do another example, and we'll end on this example, because there's only really a couple laws that we actually need to know when it comes to circuits, right? We've really been using those laws already today. Ohm's law. We've been using Ohm's law. We've been using Kirchoff's loop rule. And then we have the junction rule. So the loop rule is a conservation of energy. The junction rule is a conservation of charge. Charge is not leaking off of the wires. So I have I equals delta V over R. I have the sum of the changes in voltage around the loop equals 0. And then I have the sum of the currents into a junction equals the sum of the currents out. So these three equations are really the basis of all the circuit problems, at least mathematically. So let's just look at a little bit more of a complicated circuit. But all of them will be solved using the same method. So say I have a battery supply with 12 volts and a resistor that has 3 ohms. And then I connect it to a 6 ohm resistor and then a 12 ohm resistor. Back around. But then I also connect another resistor that has 18 ohms, and that's in parallel with the 6 ohm and the 12 ohm resistor. Okay, so in order to solve this circuit problem, the unknowns, there's really a few things that we could ask about a circuit like this. We could ask, find current, delta V, R, the voltage drop across each resistor, and the power dissipated by each resistor. Okay, that would be to solve this circuit problem. Would be to find all those things. So really, in order to do that, really what we want to do is we just want to find all the currents. Once we've found all the currents, then we can find the power, right? And we can find the voltage drop because we have Ohm's law. So basically what I want to do here in the last 2 minutes is just set up the equations. And then the answers will come from solving a system of equations. Okay, so the first step would be to label the unknowns. And the unknowns in this circuit, well, everything is unknown, but they're all related to each other, right? If I know this, I can find this. If I know this, I can find this. So the unknowns well, let me call this current. And I'm always going to label the flow of conventional current or positive charge. The flow of positive charge. I'm going to call this I1. And when I1 is going to have to be, I1 is going to have to be the same along this section of the wire because it has nowhere to go, but it can split here. So I'm going to call this I2 and I3. Remember, resistors don't use current, they dissipate electric energy. So charge is never used up, charge is conserved. So if it splits into 2 and 3 here, it has to pinch back into 1 here. So down here, it's also equal to 1. Which you can also see just by tracing this backwards. If there's if I1 is coming out this way, it has to be I1 all the way from this junction point right here. All right, so we have I could label things here. I could say, okay, here's junction 1. And here's junction 2. There's 2 different junctions in my circuit. And for junction number 1, I can write whatever comes in has to equal what goes out. So what comes in is I1. What goes out is I2 plus I3. I could write an equation for junction 2 as well. But do you see it would be the same equation? Just backwards. It'd be I2 plus I3 equals I1, same equation. That's what we call linearly dependent. It's nothing new. It's no new information. So I won't bother writing that one. And then I want to use the loop rule. And I have also an infinite number of loops I could draw here, but there's two linearly independent loops. One of those independent loops would be, I'll call this little loop, loop 1. And I'll call the big loop, loop 2, where I go around the outside edge. So I want to write two loop equations. So loop number 1, I have to choose a starting point. Let me just start here. I can start anywhere and I just go around the loop, come back to where I was. So as I cross the 6 ohm resistor in the direction of current number 2, what is the change in voltage? Is it positive or negative? It's negative. Whenever you cross a resistor in the direction of the current, you have a potential decrease. Okay, so it's negative. If I multiply R to both sides, delta V would be negative R times I. So it would be negative 6 I2. And then after I cross the 12 ohm resistor, it's negative 12 I2. And then I come to junction 2 and I want to come back along this direction. Now when I cross the 18 ohm resistor, I'm moving against the flow of I3. So is that a positive or a negative change in potential? Positive, right? Because you're going upstream now. So you're increasing your potential. So I have a plus 18 I3 equals 0. Now notice we have three unknowns, but only 2 equations. We need one more equation, and then we have a system of 3 equations, 3 unknowns. We can use, well, if you've taken linear algebra, you can solve the system of equations, or you can just do elimination of variables. Or elimination by substitution. Okay, so and then loop number 2 would be, let me start here, across the battery, going from negative to positive, corresponds to a change in potential of plus 12. And then I have minus 6 I2 minus 12 I2 equals 0. Okay, so 3 equations and 3 unknowns. So you solve for I1, I2, and I3. Right, so you have an example of doing this in your homework. And there will be problems like this that you'll see on assessments in the future. We'll end there. Is there a question, though?